Hello everyone, I'm Yiwen from the University of Michigan. Today I'm here to present Vulcan, a system we built to provide automatic query planning for live machine learning analytics. We have seen a continuous growing demand in ML analytics. Indeed, they are applied in many applications, such as video monitoring, speech recognition, and autonomous driving. In this work, we focus on live ML analytics. First, they have two unique characteristics compared to the traditional ones. First, their ML pipelines are deployed across a heterogeneous edge infrastructure instead of just sitting inside the data center. And second, besides the accuracy target of an ML inference, they often have stringent latency requirement, as most live queries requires a timely response. Because of these characteristics, serving live ML queries is not an easy task. Let me start by introducing the existing workflow of serving live ML queries, and we'll be using an example from the video monitoring query to illustrate. In the first step, users submit an input query to provide necessary information about the ML task. This includes the input data, the object of interest, which ML model to use, and some performance requirements on accuracy and latency. In our example, the input data is the live video captured by a traffic camera. The query wants to count the number of red vehicles crossing the street, and also specifies a variation of the YOLO V5 model should be used in the pipeline, along with some accuracy and latency target. When the ML expert receives the query, the next step is to construct the ML pipeline. And this step is often done based on past experience. The input here is first connected to a series of filters, which filter out unmeaningful data to improve the resource consumption in compute and network. In our example, a background subtractor is used to detect motion and filter out frames without moving objects. We also have a color filter to prevent frames without red objects from passing down the pipeline. The remaining frames will be sent to an object detector, which verifies whether the object is indeed a car. After the pipeline construction, we also need to perform and configure the pipeline by selecting an optimal set of configuration knobs which can achieve the best trade-off between query performance and resource consumption. In our case, we need to decide the frame size, the sampling rate, and which variation of the ML model to use in the pipeline. The next step is to select the physical placement for each pipeline operator across the edge tiers. In this example, the edge tiers consist of a device edge, an on-premise edge, a public MAC, and a data center. However, making the best placement choice is not easy. For example, moving the object detector closer to the device edge gives you shorter network latency, as now it is closer to the data source, but also can incur longer inference latency due to less powerful compute resource. On the other hand, moving the object detector closer to the data center gives longer network latency, but can improve inference latency, as now you can use more powerful GPUs. Finally, after the pipeline is deployed, we need to perform online adaptation to handle runtime dynamics that may affect query performance. There are two types of runtime dynamics. One is called data content change, which include changes to the input data. For example, in our query, the environment light of the scene can change based on different time of the day. And keep using the same configuration may lead to suboptimal query performance. The second type of runtime dynamics is edge resource change, which can affect the available compute and network resource across the edge. Now, the same workflow also applies to different types of live queries, such as autonomous driving and speech recognition. Of course, they will have different ML pipelines and different sets of configuration knobs, but the same elements such as filters and ML models will be there. And we also need to perform placement selection and online adaptations for them. As we can see, serving live ML queries is a complicated task that involves many steps with room for optimization. The goal of this work is to design a general system for serving live ML queries. More specifically, we have two major design objectives. The first objective is to generate optimal query plans that can optimize end-to-end latency and accuracy based on users' performance requirements while minimizing network and compute resource consumption. Here, the query plan refers to the construction, placement, and configuration in the pipeline, as we mentioned in our workflow. The second objective is to perform fast online adaptation after query deployment to adapt to any changes that might affect query performance. However, achieving these goals is not trivial as we identify several challenges. In existing solutions, query configuration and pipeline placement is optimized separately. They will first select the optimal configuration via offline profiling and then select the best placement based on the configuration they obtained in the previous step. Coming back to our video query example, they would first determine the best frame size, sampling rate, and ML model before deciding on which operator to be placed on which edge tiers. However, the query plan obtained in such an approach is suboptimal because the configuration selected in the offline profiling fails to consider the additional latency and resource consumption introduced by the placement. As a result, we should jointly optimize configuration and placement. However, such joint optimization may lead to a huge search space in our offline profiling and online adaptation stage. Another challenge we have here is in the pipeline construction. We observe that the ordering of filters in our pipeline may sometimes affect query performance. For example, switching the background subtractor and color filter in our video query may lead to a different performance characteristic, where one particular ordering may favor accuracy over latency and vice versa. Therefore, it is important that we carefully construct the ML pipeline based on users' performance requirement. However, this can lead to large profiling costs if we try out every possible pipeline to perform our joint optimization, especially when there's a high number of filters in the pipeline. To achieve our design goals and overcome these challenges, we built Vulcan. Vulcan generates optimal query plan for live ML queries by constructing the pipeline with the correct filter ordering and jointly optimizing placement and configuration. After query deployment, it also performs fast online adaptation to handle runtime dynamics. Let me start with a system overview of Vulcan before diving into its design details. When a user submits a query, Vulcan Profiler parses its content and starts its pipeline construction phase. It first constructs the initial pipeline, followed by determining the correct filter ordering. Based on the constructed pipeline, it then performs joint optimization for placement and configuration by exploring a set of promising configuration knobs for each feasible placement choice. Note that this step is done in a low-cost fashion to improve profiling cost. It then selects the optimal query plan and deploys the pipeline onto the edge. Finally, Vulcan Monitor is responsible for online adaptation by detecting runtime dynamics and performs fast reprofiling. In the interest of time, I'll focus on introducing the design choices we made in query configuration and placement selection. Please refer to our paper for more details in the remaining part of the design. The first question Vulcan needs to address is how do we determine one query plan is strictly better than another? In Vulcan, we leverage utility function to evaluate different query plans. Given a pipeline with a placement choice and a set of configuration knobs, we define our utility function to be the ratio of the query performance to its resource consumption across the edge. Here, the performance component encodes the accuracy and latency target, whereas the resource component combines the network and compute resource consumption. Under this definition, the optimal query plan is then the one with the highest utility in the entire search space. Following this logic, the goal of our query configuration process is then to efficiently search for the query configuration that can maximize our utility. In Vulcan, we leverage Bayesian optimization to perform this task. In a high level, given an objective function, Bayesian optimization is good at picking the next promising input that can maximize our objective function based on a continual observation of its output. In Vulcan, we apply BO on a per placement basis. For each feasible placement, we start a BO process to find the best configuration under that placement. In this case, the input is the configuration and the output is our utility value. For each configuration proposed by BO, we launch our pipeline, compute the utility, and feed back this value back to BO. And we stop this optimization process until no obvious improvements can be found in the utility. Although BO greatly reduces the time it takes to find the best configuration, launching the pipeline every time for a new placement is still too expensive. In Vulcan, we make the following two observations to help us explore placement choices in a low-cost fashion. First, we find that query accuracy is independent to placement. And second, the amount of data generated after each pipeline operator does not depend on where this operator is placed across the edge tiers. These observations allow us to reuse our pipeline results from the same configuration to calculate additional latency and resource consumption introduced by a new placement. Let's take a closer look at how this is done. Given a placement and configuration, if we have never seen this configuration before, we launch the pipeline offline and collect all the intermediate results. In particular, for each pipeline operator, we collect its output data size, output bandwidth, and its processing time, such that we can calculate the additional latency and resource consumption under different placement settings. For example, in the following placement choice, we can use our collected results to compute the time it takes to move the output of the background subtractor and the output of the object detector across different edge tiers. In this case, we also scale the ML inference latency in our ML model to reflect the difference in compute power across different edge tiers. When exploring a new placement with a previously seen configuration, Vulcan directly look up and reuse pipeline results to compute the utility value without relaunching the pipeline. For example, in this new placement choice, if we have already launched the pipeline before with the same configuration, we'll directly use the output side of the color filter to compute the time it takes to move the data from the device edge to the on-premise edge. Note that we also apply early pruning to quickly drop unpromising placement choices, and please find more details in our paper. Before I go over some evaluation results, I also want to briefly introduce some key ideas we have in Vulcan's online adaptation. One key observation we make here is that there's a high similarity in the input data even when runtime dynamics happen. Coming back to our video query example, things like the object of interest and where the query takes place remains unchanged as time goes by. In fact, we find that it only takes a small number of changes in the configuration to converge back to the optimal query plane during data content change. This inspires us to leverage prior knowledge from our offline profiling to perform fast reprofiling. Specifically, we apply the top K and worst K configurations as the initial data point in our BO starting point instead of using random data point as what people usually do in a normal BO process. Here, we also tune BO's parameter to make it focus more on exploitation rather than exploration because the BO has already explored a pretty good shape during offline profiling. Note that in this case, we still need to perform a placement selection to handle edge resource change. Next, we will highlight some evaluation results in the paper with a focus on how Vulcan generates query plans with low profiling cost and better end-to-end performance. You can find more experiments in our paper for a comprehensive evaluation of Vulcan. First, we present Vulcan's improvement in profiling cost when generating optimal query plans for different types of queries. Here, the vertical axis is the normalized profiling time, and we'll observe that Vulcan can greatly reduce the profiling process compared to other state-of-the-art solutions such as VideoStorm and Jelly Bean in all 3 types of queries we have tested. Regarding the end-to-end performance, Vulcan can achieve almost the same optimal performance achieved in exhaustive search. The table here shows you the normalized 99th percentile tail latency under different baseline. And we observe that Vulcan can achieve near optimal performance, but with a much smaller cost. Vulcan can also achieve near optimal accuracy results, but we don't show them here for brevity. In conclusion, serving live ML queries is a challenging task, and we share some insights on how Vulcan tackled this problem. We hope our work can provide some inspiration for future work on query planning for live ML analytics. Thank you for listening, and I'm happy to take questions.